So, continuing the development of models of the atom based on experimental evidence, there's a really exciting experiment is attributed to these two scientists, Franck and Hertz, and you've obviously heard of this person's name. But it was a big deal enough that it won the 1925 Nobel Prize. So you know that this date is around the time that all of this really interesting modern physics is happening. This was a big deal time, and it's yeah. So the Franck-Hertz experiment kind of looks like some stuff you've probably seen in our physics department, but here's kind of what it looks like. So the idea is you have this enclosed, evacuated volume of space, but inside of it is some electronics that you have sort of melted this glass thing around. And the electronics are simply just a couple of pieces of metal. So here is one piece of metal that's stuck to a wire that goes out of the enclosed glass space. Here is something, I'm going to draw it suggestively. It's like a screen called a grid, and it's just some wires that are crossed. And it's also connected to a metal lead that leaves the enclosed space, and then there's a last little metal plate like this. So yeah, so enclosed this evacuated space is this apparatus, but the apparatus is a little bit special on the outside. So so this is meant to be somewhat of a circuit. So outside is a reason to have electric field on the inside. So I'm going to draw it like this, and the idea is we get to dial, right? We get to choose this value of voltage, this potential difference between this thing that's referred to as a grid and this thing I might just describe as a source. And you notice that the negative side of the potential difference is on the left side. So the source compared to the grid is negative. So the other side, it has a battery pointed the opposite direction with a voltage that's described as a V sub 0 in your textbook. But it's also connected to an ammeter, and you know that ammeters, what they do is they measure electric current. So you notice that the orientation of this battery puts the minus on the opposite side. So it's like the grid is the top of a potential hill in a sense. Yes. And then yeah, and so this is some other sort of negativeness of charge. But the point is if you cause this source piece of metal to warm up, little electrons will shoot out of here, and they will speed up, right, accelerate, gain speed on the way to the grid, because the grid is like a positive charge compared to the source plate. But these electrons, because of this meshness of the grid, can pass through. But once they pass through, they're going to slow down. So the interesting thing that Franck and Hertz did was this, is they imagined allowing a little bit of a gas into the chamber. So so this is a little bit. So mostly it's still an evacuated space, but there is the odd atom cruising around in here. And so as these electrons move in this experiment, they have the opportunity to collide with this little bit of gas. And there's a really interesting set of experimental data that comes with this. I'll show you a picture. I'm just going to show you the textbook So here is what I just drew on the page, but this is this really interesting experiment associated with putting mercury atoms, mercury vapor atoms in there, like a gas of mercury. Honestly, this is somewhat like a fluorescent light bulb tube that's at our school. Those annoying long glass cylinder light bulbs. Yeah, so the experimental data is very interesting, and you should go and read about this experimental data. What it does is it indicates that atoms can absorb energy in somewhat discrete lumps. But what's interesting is earlier I described the Balmer's emission series. This is where atoms are, in some sense, losing an internal energy via photons or electromagnetic radiation. In this case, this is from electrons hitting atoms, and the model that this is indicating is an electron. If it's moving a little bit slow, then it's going to bounce off one of these atoms that's inside of this chamber, and the atom internally can be unchanged if this is too slow, if this voltage is too weak. There is no internal change. But if you speed this up so that an electron comes in moving, say, fast, when it hits the atom and bounces off, the electron before and after can be very different. That is, the electron coming in might be coming in with a lot of kinetic energy, but when it goes back out, it's got a tiny amount of kinetic energy left over. And the reason is because it just, in some sense, internal excitation. This is referred to as an inelastic scattering event, where there is something internal to the atom that changes, that's energetic. And the Franck-Hertz experiment is showing you that this is going to happen in this like discrete way. This is describing the quantized energy level structure of the atoms of the gas that gets put into this chamber. Yeah, so I think a really interesting point is this is not photons that are doing this. The photon picture is called absorption spectra. And it informed how people think about what's happening, say, on the outer surface of a star, or yeah. So, anyways, so these aren't photons; these are electrons, and this was kind of exciting that electrons could also, in some sense, probe, have inelastic scattering events, or probe the internal quantized excitation structure of an atom. Yeah, so the chapter finishes with a description of what's called the correspondence principle, and this is a really interesting idea. So classical physics, so pre-modern physics, so classical physics is like Newton's laws of motion, good old objects acting like particles, I guess, and the like. This kind of thinking should be where any sort of like exciting quantum or modern physics efforts, as you go, if you model systems with quantum mechanics, the idea is, or any sort of like modern efforts at thinking about nature or the physics happening, the idea is the correspondence principle, like there is nothing wrong with this, with the application of this physics if you are applying it to big enough systems. So the point is if you start off modeling small systems and imagine them as getting like taking up more space, being and the other word for this is to large quantum numbers. So we're looking at quantum numbers n that is like 1,000 or 10,000 or bigger. The idea is like these quantum models in the large quantum number limit, they start to look like classical physics models. Like one sort of quick way to see this is in the large quantum number limit, spectra do not look discrete. That is, adjacent energy levels in the large n limit, they don't have large differences between them. It's like drawing a bunch of lines. So these lines look very, very discrete because they're pretty far apart. But if I draw a bunch of discrete lines very, very close to each other, it begins to look like a continuum. And continuums are very classical. Yeah, and that's the idea of the correspondence principle. Okay. Thanks for listening.